So welcome to the course on FastSLAM. So we started with FastSLAM last week and actually introduced the key ideas of FastSLAM as well as the algorithm. And today I would like to continue where we stopped and actually look a little bit into the data association problem that rises in the SLAM problem, or especially how we can address that in a kind of nice and not too complicated way in the context of FastSLAM. So FastSLAM was a particle filter algorithm, where it uses a particle filter algorithm to implement a solution or an approach to address the simultaneous localization and mapping problem. And this particle filter typically consists of 3 steps. The first thing is the generation of the next sample set, taking into account the motion of the vehicle. This is the sampling step. Here we typically sample from a so-called proposal distribution. And in the context we had here, we use the motion model of the robot to kind of evolve the particles according to the motion of the vehicle. This is so-called the first sampling step. And then the second step is the step where we compute the importance weights of the individual particles. And what this weighting step does, it takes into account the proposal distribution that we used, so this distribution from which we generated the samples, and takes also into account the target distribution, which was the distribution that we actually want to estimate. And by using the ratio from the target and the proposal distribution, it computes the weight to account for the differences between what we want, which is a target, and what we actually use, which is a proposal distribution. In this way, it kind of reweights the samples and gives particles a higher weight. In this example here, those particles which are where their own model is in line with the observation. So those where P of Z given X has a high value. And the third step is the resampling step, where we use just kind of the standard low variance resampling step that we introduced before in the particle filter. And the idea is here to eliminate samples which have a very low weight and replace them by samples that have a high weight. And this is done because we only have a finite number of particles to approximate our distribution. And it can happen, especially if we have only a finite number, that the large number of samples kind of move away in areas or parts of the state space which have a very low probability. And to avoid that, to kind of concentrate or focus the samples on the likely regions, when you introduce this resampling step, which kind of draws particles with resampling and draws a particle with probability that is proportional to its importance weight. This is done incrementally, plus a map update step, which is also done here. The problem we have in here that the distribution, the dimensionality of the problem we are addressing is very high. These are the poses, so the trajectory of the robot, as well as the position of all landmarks. And especially particle filters are not well suited for problems which are very high dimensional. And therefore, we exploited a dependency in the state space between the trajectory of the robot, x1 to t, and landmarks L1 to Lm, by saying, if we know where the robot was at a certain point in time, or given we know that, then the mapping problem is easy. Because we could show that if we know the trajectory of the robot, the individual landmark estimates are independent of each other, so they are conditionally independent given the poses. And this allows to quite easily estimate them given we know the poses, by simply maintaining a small Kalman filter for every individual landmark. So if we live in the 2D world, it's a 2-dimensional EKF that we maintain for every landmark, and it's updated independently of the others. And why this is the case, or why we are allowed to do that, can be seen from this graphical model. We have that, so these are the poses of the robot, the different x values. We have the landmark, which are here M1 to M3, the observations V, and the controls U. And the important thing to see in here is, given we know the poses, so what's shown in gray over here, given we know those variables, there's no connection between any 2 landmarks which doesn't kind of go through a known quantity, a known variable. And this means that they are conditionally independent given we know these kind of gray shaded variables here at top. And this allowed us to model or exploit the independence between the individual landmark estimates given we know the poses of the robot. And this allowed us to kind of separate the SLAM posterior into 2 parts. So this was the original SLAM posterior about the trajectory and the landmarks. And to separate in two parts, the first thing is an estimate about the robot's poses or trajectory, 0 to t. And the second one is an estimate about the landmark locations, and since they're independent, it's an independent product. So all these guys here are modeled using an independent EKFs, two-dimensional, so low-dimensional, and this part is estimated using a particle filter. The key trick which was used is a so-called Rao-Blackwellization, where we say we have dependency between variables in the state space, and we use the sampling process only to estimate one part of the state space. In our case, these are exactly the poses of the robot. And then use that to estimate the other quantity, which is here, the map, given the poses. And since this problem is easy to solve, we just need to sample this posterior over here, so the first one, and then compute the landmark estimates individually for every particle. So every particle carries its own set of EKFs to estimate the landmark locations. And that means that every particle has its own map. That was kind of the key idea of the Rao-Blackwellized particle filter for SLAM. And the first one who actually implemented this idea in an efficient manner so that the working system, what the outcome was Mike Montemello, 2002. So every particle, it's kind of sketched here, has its pose estimate, x, y, theta, and landmark estimates. And these landmark estimates are small 2x2 Kalman filters. And so then you can actually run this particle filter. The system samples only the poses, the particles, and then updates the map according to the sampled poses, and in this way has a multimodal belief about it, including the trajectory and the landmark estimates. But the important thing to note is every particle has its own landmarks, and this only can be done efficiently because these landmarks are 2x2 Kalman filters. If these dependency couldn't be exploited, these guys would need to be high-dimensional Kalman filters, and then this would be typically very hard from a computational point of view. The key steps of the FastSLAM or FastSLAM 1.0 algorithm was we sample the poses according to the motion model, so according to how the robot moves. Then we compute the updated weights according to this formula. This is the weight formula, and we actually derived why this is the weight formula last time. This comes because we take the target, divided it by the proposal, and then did some derivations. So we ended up here. And then we update the belief of the observed landmarks using the standard EKF update rule, first 2x2 Kalman filters. And actually these two steps are typically done jointly in the joint step. And then we have the resampling step at the last round. We also showed a small video, in the video provided by Mike Montemello, where you see the robot moving around. Should see the robot moving around. Okay, here we go. And so we have the blue line, which is the ground truth trajectory, the red line, which is the estimated trajectory, and the dashed line, which is the odometry. And you see the landmark poses, so the blue dots are the true poses because this is done in simulation, so you knew where the landmarks are in reality, and the estimates that the FastSLAM algorithm actually provides. And kind of these half of a circle area here is kind of the visibility range of the robot at the core point. You can see actually that there's sometimes a deviation between the ground truth estimate and the estimate of the next particle, but all in all, it matches significantly or substantially better than the odometry estimate we have here. One of the key things in the particle filter step, particle filter for applications in general, is how to design a good proposal distribution. And here, you just said we use the motion model as our proposal distribution, similar or exactly the same way as this is typically done in Monte Carlo localization. And if we do so, we need to compute the importance weights, and this is computed as the target distribution divided by the proposal distribution. We did some derivations in here and calculated for a couple of minutes, and then we'll be able to show that this is approximately this distribution over here. So under the assumption that we have Gaussian distributions involved, under some linearization assumptions, we end up that this is the way we compute our importance weight. And what it actually means is, so this is the observation we actually obtained, VT, and we have the head, which is the expected observation. And here now the expected observation is computed for every particle individually, because every particle has an own pose estimate and an own net estimate. So every particle computes its own expected observation. And then we simply evaluate how well does the expected observation actually matches the real observation. So if they are identical, that means the estimate that the robot has about its own pose and the world is pretty close to what we actually measure. So this is a particle that should get a high weight. And if this term goes to 0, this value, the whole overall expression is maximized. And the Q here was the uncertainty associated to the observation, and so the measurement covariance, taking into account also the another part of the distribution. So we have that the uncertainty of the landmark in the current estimate of the particle filter, so the sigma of the individual 2x2 Kalman filter, transformed through the inverse of the Jacobian, this nonlinear function, plus the uncertainty we associate to our observation. So it combines the uncertainty we have in the map and the uncertainty of the measurement. So the more uncertain the robot is about the landmark in its map, the smaller the contribution to the particle weight, which is what you would expect. If you perfectly know where the landmarks are, then it would be only the uncertainty or the noise in the observation you would take into account. And this is exactly what is done here. So this is kind of the explanation what that weight means. So the better the estimate that the particle does fits with the world, so with what the robot physically measures, the higher the weight. The bigger the difference between the map and the pose estimate of the robot compared to the real world, the lower its weight. It's kind of the kind of intuitive explanation of this distribution. So that's where we actually stopped last time. So everyone should have an idea how the FastSLAM algorithm works, what are the key steps which are done, and they throw us the key ideas. And if we do so far, in all our approaches we said, we use known correspondencies. So we know when we observe a landmark, that this landmark we observe is actually landmark, whatever, number 18 in our map so far. This, of course, is a pretty strong assumption that we make, that we have this known correspondency, or that the data association problem is basically non-existing because we know the perfect idea of every landmark. That's the assumption we did so far. We did in the common filter-based approaches, and we did in FastSLAM 1 so far. But FastSLAM has a nice property which allows us to address the data association problem in a really nice way. So the data association problem can be illustrated by this example. So let's assume this is the position of the robot, and we have 3 landmarks in the environment, and we get 2 observations, which are these green dots over here. So one data association hypothesis could be illustrated by the blue arrow. So this green measurement corresponds to this landmark, and this green measurement corresponds to this landmark. Oh, sorry. Or the other way around, that the red arrows indicate the correct data association. So this guy corresponds to this landmark, and this guy corresponds to this landmark. These are the 2 most likely ones. Depending on the noise we have in our sensor, it may even be the case that this one belongs to that one, and this one belongs to that one, or whatever. There's a new landmark we haven't observed yet. So there's a large number of possibilities that actually can appear. The 2 most likely ones are the ones which are depicted here in red and blue. So the problem is we have more than one data association, and there are even situations where we have 2 possibilities where one is not more likely than the other one, or at least in the current state we cannot say association 1 is better than association 2. And moreover, the pose of the robot influences the data association. So if this robot would be a little bit more rotated to the left, the blue association would be the more likely one. If it would be rotated a little bit more to the right, the red association would be the most likely one. So the pose of the robot has a strong influence on the likelihood of the individual associations. And this is why data association is complex, or one of the reasons why it is complex. But in the particle filter, we have a very, very nice setup and are able to actually address this problem in a rather efficient way. Does anyone has an idea what we can do in the particle filter setup to address the data association problem in an effective manner?
Just add another particle for different types of data association.
That would be one solution to actually, if we have a particle and we have this high ambiguity, you just duplicate the particle. And say if one particle makes association red and the other one makes association blue, and we continue with that. It's a pretty smart idea, but it's perfectly fine. What's the problem with this technique? Yes, in which way it is expensive?
But if you have multiple possibility solutions, then you will have the particle numbers will increase quickly.
Exactly. So especially if we have a sequence of data associations which have ambiguities, this leads to a dramatic increase in the number of samples to maintain. But the idea is already very good. This actually, we do an approximation of this idea. That's what FastSLAM does. Okay, so let's have a look. How does the distribution, or anyone else has an idea on what you can do?
I can count how many particles have the same data association, where the landmarks are close to the observation.
That's also something we could do. So we could estimate, just would look, how does the pose estimate of the individual particles influence a decision, and then make one decision globally by saying, let's say, 80% of the particles say this is more likely, and 20% say this is more likely, and that makes association. But actually, no one forces us, compared to the EKF, to make the data association globally for the whole system. The particle filter actually has the ability that it can make individual data association decisions for the individual particles. This is kind of the key strengths that we can also have a multimodal belief about data associations. So the key thing is we can make decisions on a per particle basis. We can say, in particle 1, we go for the red estimate, and for particle 2, we go for the blue estimate. No one forces us to have one single global data association decisions which is made in the particle filter. We can really do it on a per particle basis, and this is one of the big powers of the particle filter. So for example, one of the samples over here begin at, let's say, 3 landmark estimates which are roughly triangular shaped. And let's say for the particle which is sitting over here, this may look like this. For this particle, that's actually a very likely data association. So this particle is quite likely it's going to make this decision over here. If you, however, have a particle which sits down here, the decision may be different. Although, I mean, of course, they get the same physical observation. But for a particle somewhere down here, this association is much more likely. And if you have a particle somewhere in the middle, there may be other combinations which are possible. So the big advantage is that we can do the data association on a per particle basis. So particle 1 can say, for me the most likely configuration is that this observation belongs to this landmark. Particle number 2, which may be located somewhere more over here, can say, this observation belongs to the other landmark. This is a key strength. So we can do the data association on a per particle basis, and for every particle, we don't have any pose estimate. Because if you remember, every particle can be seen as a trajectory hypothesis, and every particle for itself says, I did the right estimate, the right job, everyone else is wrong. It's kind of the assumption which is associated with every sample. What every sample, if you would consider the sample as an individual entity, would claim about itself. So, since every particle says, I did the right job, everyone else is wrong, it says, for me, this is the data association. So the pose estimate is not existing anymore in the data association problem for an individual particle. The individual particle only reasons about, let's say, the noise in the observations, and maybe the noise or the error in its estimate, or uncertainty it has in its estimate so far, and can make the data association based on that. So it's a much simpler form of data association, because every particle can assume a 0 post uncertainty. And then the data association problem is simpler. That's actually what the particle do. So what we can do is do an individual per particle data association, assuming that the current estimate of that particle is the right estimate. And since we have multiple particles and every particle makes its own decision, if we look to the global posterior, or the posterior as a whole, we still have multimodal belief, because, let's say, 20% of the samples do decision 1, 20% do decision 3, and 60% do another decision. So we get this multimodal belief in a global sense, but not on a per particle basis. Okay, how does this look like? So assume we have a robot, and we have the red and the brown covariance estimates for landmarks that the particle has in its own map. And it observes this landmark here, just a single landmark. What should we do? What should we update? There are different ways we could address the problem. If you, let's say, the observation likelihood given the map, given the red landmark, is in this case 0.3, and the probability for getting that observation given it is the brown estimate is 0.7. So what would be good ideas given this information to actually make the data association? What would be good strategies from your point of view?
Difference between expected observation and real observation.
So this is
less we can trust.
That's the most simple approach. It needs to be simply to the distance, so the difference between the expected observation and the obtained observation. However,